We turn now to trigonometric substitution. The purpose of this topic is to be able to integrate expressions of the forms that you see here, how we have either a squared minus x squared minus a squared, or x squared plus a squared. Just to think about why we would need to do this, recall that if we had an expression like this, like 2x square root of x squared plus 1. This was something that could easily be solved by u substitution, where we'd simply set u equal to that and du equal to 2x dx. And we can see that then we'd be able to clear all the terms in this integral. The problem is if instead I had started with, let's say, the integral of square root of x squared plus 1 dx, that trick wouldn't work because that depended on us being able to get a 2x, so that there was a 2x somewhere in the integral, or at least some factor of x that we could easily clear out. So we're going to need a different technique to make this work. And the way we're going to do it is we're going to leverage the fact that expressions like a squared minus x squared look very much like 1 minus sine squared. So what we're going to use is what's called a trigonometric substitution, where we're going to replace x with a trig function in order to be able to find the integral of the given expression. In addition to actually seeing how to evaluate these integrals, one thing that I think is useful about this unit is that it turns out that once you look at the way the trig substitution works, I think it becomes a little bit more clear why the antiderivatives of certain functions are the inverse trig functions, or conversely, why the inverse trig functions have certain derivatives. We know, for example, that the derivative of tan minus 1x is 1 over 1 plus x squared. And I think that the connection between those two becomes a little bit more apparent.